From this video, you will understand how to find the solution of the wave equation when there is triangular initial deflection. So then this triangular initial deflection is given by this function fx equal to 2k by L into x when x lies between 0 and L by 2, and fx equal to 2k multiplied by L minus x by L when x takes value between L by 2 and L. So first of all, we can see that both of these functions are first degree in x. Therefore, it represents straight line. So now consider this end point. So when x is equal to 0, then fx is 0. So when you substitute x 0 here, we will get 0. And now when x is L by 2, fx is 2k by L multiplied by L by 2, that is k. So that means the point corresponding to this x value L by 2 is k. That means this is the point L by 2 k, and this height displacement is k here. So then this is the straight line which represents the function 2k by L x, that is valid from 0 to L by 2 when x takes values from 0 to L by 2. Now consider the second case. So here when x is equal to L by 2, we will get the same point k. Then consider this point L. When you put L, x is equal to L, we will get 0 here, that is this point. So then when x is equal to L, we will get 0. That means this is the straight line which represents the function 2k L minus x by L. So this is the graph of the triangular initial deflection which is given by this function. Now then we will find out solution of this equation with this initial condition. For that I have written the wave equation here. So displacement of the string is described by the one-dimensional wave equation which is given by the first equation, and here boundary conditions. So boundary conditions means the displacement at the point A and B. So we can write it as u 0 t. So at this point displacement is 0, and at the point L, that is u L t, is also 0. So they are boundary conditions. So it is written here boundary conditions are these two, and now we will write initial conditions. So then initial condition means we have to write down u of x 0, that is the initial displacement. Also we have to write dou u by dou t at the point t equal to 0. So this is initial deflection and this is initial velocity. So then in the question it is given the initial deflection as this f of x, and then we can understand that initial velocity is 0. So therefore these are the initial conditions. U x 0 is f of x, that is given by this function, and also initial velocity is 0. Now then we know the solution of the wave equation, one-dimensional wave equation is u of xt is c1 cos px plus c2 sin px multiplied by c3 cos cpt plus c4 sin cpt. So then our aim is to find out c1, c2, c3, c4, they are the constants for this particular problem. So then in the previous problem I have explained how to find how to apply these boundary conditions. Here also boundary conditions are same. So then as in the previous problem, after applying boundary conditions and applying the principle of superposition of solutions, we can see that u x t equal to summation n minus 1 to infinity sin n pi x by L an cos n pi ct by L plus bn sin n pi ct by L is a solution of the given problem. So now this fifth equation contains two constants an and bn. Now using the initial conditions we will evaluate an and bn. For that we have two initial conditions, that is represented by 3. So then here the second initial condition, the right hand side value is 0. So therefore I will apply the second initial conditions first. So now consider the initial condition, dou u by dou t at the point t equal to 0 is equal to 0. So for applying this one we have to find out dou u by dou t. For that differentiate fifth equation partially with respect to t. So that dou u by dou t is equal to summation n varies from 1 to infinity sin n pi x by L. Then while differentiating we will get one constant here as a common factor. So we can write it as n pi c by L, that is the coefficient of t of this cos function and sine function, okay, coefficient of the argument, okay. So then n pi c by L multiplied by minus an sin n pi c t by L plus bn cos n pi c t by L. So now in this equation we put t equal to 0. So when you substitute t equal to 0, dou u by dou t is 0, that is our initial condition. So 0 equal to summation n varies from 1 to infinity sin n pi x by L n pi c by L. Here sin 0 is 0. When you put t equal to 0 we will get this term as sin 0, that is 0, and here we get cos 0 and cos 0 is 1. So we got one more term here, that is bn. And now the right hand side series is equal to 0. So then this becomes 0 only if bn is 0. If bn is not 0, this is not possible. Therefore this implies bn is 0. So we got one coefficient in our solution given by fifth equation. So here in the fifth equation we can put bn equal to 0, so that we will get only one term in this one. So now we can write, therefore 5 becomes equation 5 becomes u x t is equal to summation n varies from 1 to infinity sin n pi x by L multiplied by an cos n pi c t by L. This is our sixth equation now. So now this contains only one coefficient an. So we have to evaluate this an. For that we consider the initial condition. Only one more condition we have to apply in this problem. So consider the initial condition, that is given as u x 0 is equal to f of x is equal to 2k by L x when x takes values between 0 and L by 2, and the second condition is, second value is 2k L minus x by L when x takes values between L by 2 and L. So therefore for applying this one in this equation we take t as 0. So put t equal to 0 in sixth equation. Here we get u x 0 and ux0 is f of x. So, f of x is equal to summation n varies from 1 to infinity sin n pi x by L a n, then this term cos n pi ct by L, but here t is 0, so that this becomes cos 0 and the value for cos 0 is 1. So, we will get only a n here, and now I will rearrange this term here. So, we can write this as fx is equal to sigma n varies from 1 to infinity a n sin n pi x by L. And now we know that this takes the form of a half range Fourier sine series, of f of x. So, therefore, we can find out Fourier coefficient a n here. So, therefore, a n can be written as the formula for calculating the Fourier coefficient in half range Fourier sine series is 2 by L integral from 0 to L f of x sin n pi x by L dx. Now, for evaluating this a n, we have to substitute fx here and then we have to integrate. But here fx takes two different values in two different intervals. So, we will split this integral into two and we will write the value there, so that we can write this as 2 by L. First integral limits are from 0 to L by 2 and the value for kx is fx there is 2 kx by L sin n pi x by L dx. That is the value of f of x in the interval 0 to L by 2. Now, the second integral, limits of the second integral are L by 2 and L, and the value for f of x is 2k L minus x by L, then multiplied by sin n pi x by L dx. So, now we have to integrate these two functions. So, here you can see that this contains two functions, product of two functions. See, the first function is a polynomial. Here we can consider this 2k by L as a constant common factor, and here also we have the same term. So, I will write it outside this integral sign, so that it becomes 4k by L square. And now see this integral, here it is x into sin n pi x by L. Since the first function is a polynomial, I will use the generalized rule here. So, first function, so formula that rule is like this: for finding integral of x multiplied by sin n pi x by L, the rule is first function x into integral of the second, that is minus cos n pi x by L divided by n pi by L, then minus here. Now, you write down derivative of the first term x, that is 1 into now integral of this second function. So, it is minus sin n pi x by L divided by n pi by L the whole square. So, this is the integral of the first term, and now limits are from 0 to L by 2, and there is one more integral. So, I will write here plus here, then 2k by L I have written outside of the bracket, and the function is L minus x, that is also a polynomial. Again I will use the generalized rule here, because polynomial into trigonometric function. Okay. So, that is L minus x, first function, into integral of the second, that is minus cos n pi x by L divided by n pi by L minus, now derivative of the term L minus x, it is minus 1. Now, integral of the second term, that is minus sin n pi x by L the whole divided by n pi by L whole square. Now limits are from L by 2 to L. So now we have integrated both integrals. So now next step is applying the limits. So then here you apply the upper limit, that is L by 2, so that we will get, when you substitute L by 2 here, you will get cos n pi by 2, that is 0, and here we will get sin n pi by 2, so that is not equal to 0, so we will get value from here. So therefore this is equal to 4k by L square, and now that minus minus becomes plus, so we can write sin n pi by 2 divided by n pi by L the whole square. And now the lower limit is 0 here. So when you put x equal to 0, this term is 0, and here you put x is equal to 0, we get sin 0, that is also 0. So value of these two terms at the lower limit is 0. Now then compute the second bracket, here L minus x. Okay, so then upper limit is L here. When you substitute L here, you will get L minus L, so it is 0. And now lower limit, when you put x is equal to L, we get sin n pi, that is also 0. Therefore, value of the function at the upper limit is 0 minus, now we will write down value of the function at the lower limit L by 2. So when you put x is L by 2 here, we get sin n pi by 2, which is 0, and now from here minus sin n pi by 2 whole divided by n pi by L the whole square. So now these two terms are similar terms, so that we can add these two, so that we get 4k by L square multiplied by L square by n square pi square, then 2 times sin n pi by 2. So we can write this as 8k by n square pi square sin n pi by 2. So this is the value of an, and now we can observe that when n is an even number, you will get sin as 0. Therefore, an has non-zero value only if n is an odd number. So we can write an in this form. An is 8k by n square pi square sin n pi by 2 when n is an odd number, and 0 when n is an even number. So this is the value of constant which appears in the solution of the given problem. So the solution we have written here, that represents sixth equation. So what we can say is that the solution of the given problem, that means one dimensional wave equation having triangular initial deflection, is uxt equal to summation n varies from 1 to infinity sin n pi x by L an cos n pi ct by L, where an is given by the last equation. So I will write it here. So I will take this as equation number 7. Therefore, solution of the given problem is uxt is summation n varies from 1 to infinity an sin n pi x by L cos n pi ct by L, where an is given by equation number 7.